In this lesson, we will continue our study of power series representations of functions, and we'll also discuss some of their applications. So find a power series representation for the following functions and determine the interval of convergence. So remember, this is a lot like a geometric series. So we can think about this function in particular as x squared times 1 over 1 minus negative x. And you can think about this as x squared times the sum from n equals 0 to infinity, negative x to the n, or x squared times the sum from n equals 0 to infinity, negative 1 to the n, x to the n, which is the same thing as the sum from n equals 0 to infinity, negative 1 to the n, x to the n plus 2. I guess you could have also thought about this as x squared over 1 minus negative x, and that could have also been thought of as a geometric series where your a is equal to x squared and your r is equal to negative x, and you get the same answer. You get the sum from n equals 0 to infinity, x squared times negative x to the n, which is the same thing as the sum from 0 to infinity, negative 1 to the n, x to the n plus 2. So it doesn't matter if you multiply the x squared through later or you think about it as being part of the a in the beginning. Now to find the interval of convergence, we look at the stage at which we used a geometric series, which is this stage. We need the absolute value of negative x to be less than 1, which is the same thing as saying negative 1 is less than x, which is less than 1. And if you have not integrated or differentiated that geometric series, the end-to-point convergence will not change. So there's actually no need to check, but that is the interval of convergence. If you want to check the endpoints and be 100% certain, you could. Both will diverge by the test for divergence. All right, similar idea. In this case, we also have something that's geometric-ish. The a is 5, and the r, it appears, is actually 16x squared. So this is the sum from n equals 0 to infinity, 5 times 16x squared to the n. Same thing as the sum from 0 to infinity, 5 times 16 to the n, x to the 2n. And this will converge if the absolute value of 16x squared is less than 1, or the absolute value of x squared is less than 1/16. And for that to be true, your x must be between negative 1/4 and positive 1/4. And similar idea here, we just use the geometric series. If you want to check the endpoints, you're going to have that they diverge by the test for divergence. We also found power series representations for these functions. This one was the sum from n equals 0 to infinity, negative 1 times x to the n plus 1 over n plus 1. And that was true if negative 1 was less than or equal to x, but less than 1. Now just a note that your book actually re-indexes this and writes the series like this. They write it as the sum from n equals 1 to infinity, negative 1 x to the n over n. If you want to write out the first 3 or 4 terms and convince yourself that those are the same thing, you could, but they are. And then we also had a power series for inverse tangent. Well, this was the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, and the interval of convergence there was x had to be between negative 1 and positive 1, inclusive of both endpoints. Using those power series we know, let's find a power series for these more complicated functions. So we'll have x cubed times the power series for inverse tangent with x squared plugged in for x. So that will be the sum from n equals 0 to infinity, negative 1 to the n, x squared to the power of 2n plus 1 over 2n plus 1. Now those exponents multiply, giving us x to the 4n plus 2 over 2n plus 1. And when the x to the third goes inside the series, the exponents on the x's add, giving us a sum from n equals 0 to infinity, negative 1 to the n, x to the 4n plus 7 over 2n plus 1. And then ln of 1 plus 2x. Well, we have a power series for ln of 1 minus x. So let's express that as natural log of 1 minus negative 2x. And now we know to input negative 2x for x into our power series for ln of 1 minus x. So that's a sum from n equals 0 to infinity, negative 1 times negative 2x to the n over n plus 1, which is the same thing as the sum from n equals 0 to infinity, negative 1 to the n, 2 to the n, x to the n, over n plus 1, or final answer, sum from n equals 0 to infinity, negative 1 to the n plus 1, 2 to the n, x to the n, over n plus 1. Now remember, we can also differentiate and integrate power series. We'll talk about how we do that. So if we want to differentiate this power series, this part is constant. The part that gets differentiated is the part that has the x. So with the derivative, the first term, the c naught term, will be gone because the derivative of a constant is 0. So this will be the sum from n equals 1 to infinity cn. The derivative of x minus a to the n is n x minus a to the n minus 1 power. And then for the antiderivative, the sum from n equals 0 to infinity, cn, the antiderivative of x minus a to the n is x minus a to the n plus 1 over n plus 1 plus some constant c. The few examples we had in the last lesson, we found this c to be 0. In this next example, we will find c not being 0. Find a power series representation for f of x, which is ln of 4 minus x, and give its interval of convergence. So there are two ways to do this. You could actually use the formula for ln of 1 minus x if you're clever, and so I will show you both ways. So the first thing to notice is that the derivative of ln of 4 minus x is negative 1 over 4 minus x. So the antiderivative of negative 1 over 4 minus x will equal ln of 4 minus x plus some constant c to be determined. So we'll say, well, ln of 4 minus x equals the integral of negative 1 over 4 minus x, which we can find a power series representation for. So that's negative 1 over 4 over 1 minus x over 4, or the integral of the sum from n equals 0 to infinity, negative 1/4 times x over 4 to the n, which is the same thing as the sum from n equals 0 to infinity, negative 1 over 4 to the n plus 1, x to the n. It is best before you integrate to simplify that down so you have as simple of a x to a power as possible. You could have technically anti-differentiated right here, but it's a little bit more tricky to get it right, and most students who try don't actually succeed. Now, this stuff is a constant. This is the thing you integrate. So we have the sum from n equals 0 to infinity, negative 1 over 4 to the n plus 1, times x to the n plus 1 over n plus 1 plus some constant c. Now let's figure out what that c is. When you input x equals 0, we get ln 4 equals c. So our power series representation is the sum from n equals 0 to infinity, negative 1 over 4 to the n plus 1 times n plus 1, and the numerator x to the n plus 1 plus that ln 4 hanging out on the end. So that's one way. Another way, if you want to use the series for ln x, this is a little bit clever, but it actually is easier. So you have representation for ln of x, ln of 1 minus x. You need to get rid of that 4. So write this as ln of 4 times 1 minus x over 4. And then use properties of logs to expand that into ln 4 plus ln of 1 minus x over 4. Okay, that ln 4 is just a constant, it hangs out. We'll have plus the sum from n equals 0 to infinity. Now plugging in x over 4 into our formula for ln, we will have negative 1 times x over 4 to the n plus first power all over an n plus 1. That's the same thing as ln 4 plus the sum from n equals 0 to infinity, negative 1 x to the n plus 1 over 4 to the n plus 1, and that other n plus 1 is also in the denominator. And notice that this is the same thing we got in the previous slide. Personally, I think this way is a little bit easier, but it's a little bit tricky because you have to account for properties of logs. And also notice that ln 4 we found is the constant c after integration. There it is. It's here as well, so that was really not a fluke. All right, now some common applications of power series are finding antiderivatives for and approximating definite integrals for functions when you cannot find the antiderivative by conventional means. So evaluate this integral using a power series. So we have the integral of 1 over 1 plus x to the 7th dx. Well, let's say that is the integral of, we can express that 1 over 1 plus x to the 7th as a power series by writing it as 1 over 1 minus negative x to the 7th. So that's the same thing as the integral of the sum n equals 0 to infinity negative x to the 7th to the n, or the integral of the sum from 0 to infinity negative 1 to the n x to the 7n dx, which is the sum from n equals 0 to infinity negative 1 to the n. We antidifferentiate this x to the 7n. We have x to the 7n plus 1 over 7n plus 1 plus some constant c. So there is an antiderivative of f of x, and that may have a nice, clean form, but we don't know, so whatever, there's an antiderivative. And we're going to use it to estimate this particular definite integral correct to within 10 to the negative 7th. So holy moly, you think that that's like really accurate. Maybe we're going to need a lot of terms, and how does it relate? It's not clear, but here we go. So the integral from 0 to 0.5. So first thing is the plus c is not needed. So this will equal the sum from n equals 0 to infinity negative 1 to the n x to the 7n plus 1 over 7n plus 1 evaluated from 0 to 0.5. Well, plugging in 0 will just give us a whole bunch of zeros. So really all we do is we plug in 0.5 for x. And we have a sum from n equals 0 to infinity, negative 1 to the n, 1/2 to the 7n plus 1 over 7n plus 1, or the same thing as the sum from 0 to infinity, negative 1 to the n over 2 to the 7n plus 1 times 7n plus 1. And we can use the alternating series remainder test to estimate the error. So we want the remainder, which is less than or equal to the n plus first term, and plugging in n plus 1, we will have 1 over 2, 7, n plus 1 plus 1 times 7 n plus 1 plus 1, which is the same thing as 1 over 2 to the 7n plus, let's see, 8 times 7n plus 8. And you can input various n's, and you want this to be less than 0.1234567 Okay, so small. Okay, and when you do, if you just input n equals 3, that is actually sufficient. With n equals 3, R3 is less than or equal to the fourth term, and when you plug in 3 into this for n, or plug 4 into this original expression, you get 1 over 2 to the 29th times 29, which is 6.4 times 10 to the negative 11th. Those terms get small really quickly. And so your integral, which I'm going to call I, is about equal to the sum from n equals 0 to 3, negative 1 to the n, 2 to the 7n plus 1, times 7n plus 1. Notice that this means you're actually plugging in 4 things, because first you plug in 0, then you plug in 1, then you plug in 2, then you plug in 3. That'll be 1/2 minus, plugging in 1, we have 8 times 2 to the 8th. Plugging in 2, we have 1 over 15 times 2 to the 15th. And plugging in 3, we have 1 over 22 times 2 to the 22, which is about equal to 0.4995137 What's kind of amazing is you only need 3 terms to get what I would consider quite good accuracy. If you add in very many more terms, you're going to have amazing accuracy. All right, let's just first find some integrals, and then we'll use them to do some approximations. So evaluate this as a power series and find the radius of convergence. So first, let's express this as x over 1 minus negative x cubed. And that can be thought of as a geometric series with our a is x and our r is negative x cubed. So x times negative x cubed to the n. And before we integrate, let's sort of write x to 1 power. So we have negative 1 to the n, and then x to the 3n plus 1. So now we antidifferentiate the x to the 3n plus 1. We have the sum from n equals 0 to infinity, negative 1 to the n, x to the 3n plus 2 over 3n plus 2 plus some constant c. And we're only asked to find the radius of convergence. So this will converge if the absolute value of negative x cubed is less than 1, which implies that the absolute value of x cubed is less than 1, and that will be true for x's between negative 1 and 1. And so since the total width of our interval is 2, the radius of convergence, r, is just equal to 1. If you want to test both of the endpoints, you're going to find that they both converge by the alternating series test. All right, arctan of x over x as a power series. So, holy moly, this seems like it might not be possible. We'll give it a shot. Inverse tangent of x over x. Well, we know that's the same thing as 1 over x times the sum from n equals 0 to infinity. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So I multiply that 1 over x through the exponents, subtract, just giving me x to the 2n. So I have the integral of the sum from 0 to infinity. I'm going to take the negative 1 to the n and the 2n plus 1 and separate them off because they're a constant multiplied by x to the 2n. And we can differentiate x to the 2n, anti-differentiate. We have the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1 over 2n plus 1 plus some constant c, or the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1, the quantity squared, plus that constant c. So there is the antiderivative of that function. There's no other way to do that at this stage. You guys don't know any other methods that work, and I'm not aware of them either. Okay, so the radius of convergence, this will converge if, well, the absolute value of x is less than 1, because that was the radius of convergence of inverse tan. So we have that r is equal to 1. If you want to, you can test the endpoints and you can verify that this series converges at both negative 1 and positive 1. Now let's actually use our results to approximate some integrals correctly to a certain number of decimal places. So in the previous slide, we actually anti-differentiated this function. This time we just care about the integral from 0 to 0.3. So the antiderivative of x over 1 plus x cubed was the sum from n equals 0 to infinity, negative 1 to the n, x to the 3n plus 2 over 3n plus 2. We don't need the constant c because we have a definite integral, evaluated from 0 to 0.3. And plugging in 0.3, plugging in 0 doesn't matter because you get 0. The sum from n equals 0 to infinity, negative 1 to the n, 0.3 to the 3n plus 2, all over 3n plus 2. And just note here that 0.3 is less than 1, so we know that this series will converge. That number has been plugged in for x, and this series has domain x must be between negative 1 and positive 1. Okay, so that is our exact answer. We want to approximate this correct to 6 decimal places. So notice we have negative 1 to the n, so we're using the alternating series remainder theorem. So that says that the absolute value of Rn is less than or equal to the absolute value of the next term you leave off. And I'm just going to write down what that term is. That's going to be 0.3 to the power of 3 times n plus 1 plus 2, all over 3 times n plus 1 plus 2. We want that to be less than 0.1, 2, 3, 4, 5, 6 zeros and a 5. That will guarantee we have 6 matching decimal places. And it turns out that when you plug in various numbers for n equals 3 is the first number that works. So your integral I will be about equal to, so first we plug in 0, that's going to be 0.3 to the second over 2. Then we plug in 1, we'll have 0.3 to the 5th over 5. Then we plug in 2, and we have 0.3 to the 8th over 8. And we plug in 3 now. Oops, and that should be a minus since we have flip-flopping happening. So minus 0.3 to the 1, 2, 3, 9, 10, 11 over 11. And that's about equal to 0.044522. Last one, let's use a power series to approximate this correct to 6 decimal places also. And so the only problem here is we don't actually know a power series representation for this function. So, well, we should be able to find one. Let's think about this as x times ln of 1 minus negative x squared. So that's x times the sum from 0 to infinity, negative 1 times negative x squared to the n plus 1 over n plus 1. So that's the sum from n equals 0 to infinity. We'll have negative 1 to the n plus 1, x to the 2n plus 2 times x all over n plus 1. And that's the same thing as the integral from 0 to 0.2, the sum from n equals 0 to infinity. This could be thought of as negative 1 to the n, x to the 2n plus 3, and we have over n plus 1. And now we antidifferentiate x to the 2n plus 3. We have the sum from n equals 0 to infinity, negative 1 to the n over n plus 1, times x to the 2n plus 4 over 2n plus 4, and that's going to be evaluated from 0 to 0.2. And that will give us the sum from n equals 0 to infinity, negative 1 to the n, 0.2 to the 2n plus 4 over n plus 1 times 2n plus 4. Now, amazingly enough, so that's the definite integrals expression. Now let's figure out how many terms we need to have this correct to 6 decimal places. So notice once again that we have an alternating series. So we're going to use the alternating series test remainder. So where the remainder is absolute value is less than or equal to the n plus first term. And the n plus first term, once it's been absolute valued, will be x to the 2 times n plus 1 plus 4. And that x will actually be 0.2. All over n plus 1 times 2 times n plus 1 plus 4. Or 0.2 to the power of, that'll be 2n plus 6. In the denominator we have n plus 2 and 2n plus 6. And amazingly enough, n equals 1 works. So we need this to be less than 0.1, 2, 3, 4, 5, 6, and 5. And n equals 1 actually ensures that we do this. So then our integral I will be about equal to just the sum of the first two terms. So first plug in 0, and we have 0.2 to the 4th over 4. Then plug in 1, and we'll have 0.2 to the 6th over 2 times 6. which is about equal to 0.000395. And the only way to sort of find these numbers of terms used is to get yourself an expression for the general n plus first term, have a threshold value you need it to be less than, and just plug in different numbers for n until you find one that works. It usually won't take very many, so aim kind of low. If you want to start with like n equals 2 or n equals 3 and you find that that works really well, you could go lower and check if one lower works. WebAssign might not have a threshold to accept something. Like you can't always pick n equals 1,000,000. That's just silly. So the idea is find the smallest n such that you get this inequality to be true.